All right, so now that we are familiar with what a vector valued function is, it's time for the calculus. But as I've been saying, the calculus works exactly the way you want it to work. So basically, if you understand vector valued functions and if you understand differentiation and integration, you can do this. There's a few little, bumps along the way, but honestly, they're pretty easy to deal with, in my opinion. All right, so let's start with differentiation. All right, so we have a vector valued function r given by, some function of x times I hat plus some function of y times j hat. And notice what this says right here, that to find the derivative of your vector valued function, all you do is differentiate each of the individual components, right? So to get the derivative of the vector function r, differentiate your I component, differentiate your j component. It's that simple. Or, if you're in 3 dimensions, okay, then you're differentiating each of your 3 components. But the idea still holds. So I would say that that's the big takeaway from right here, is that you simply differentiate each component function. Again, works exactly the way that you want it to work. So let's get to it. So with the first example here, we are given a vector valued function, and the first instructions are to just sketch the plane curve by finding a rectangular equation. All right, so right now, I think it will be helpful, right, to identify what our component functions are, right? We know that in general, a vector valued function looks like this. Some function x, right, times I hat, plus some other function of t times j hat. So here, it's not too hard to see that this is x, right? And this right here is y. Okay, so in other words, the component functions are defined as such, right? X of t is t. Y of t is t squared plus 2, right? But from this first one, right, that's basically, right, we could say x of t, or we could just say x, right? The of t part of that is really just a good math manners thing, right? So x equals t. So now we are able to use that relationship to explicitly get y as a function of x, right? If y is t squared plus 2 and t is x, then it must be the case that y equals x squared plus 2. So this was a very simple parameterization of a parabola. Been seeing a lot of parabolas with this. So let's draw it. Okay, and we know that this point right here is 0, 2. Here's our parabola. And if we think about indicating trajectory, all right, I mean, pretty much in this case, t is going to increase as x increases because t and x are equal. So we are pretty sure that our trajectory will be from left to right. Okay, great. All right, so great. We have sketched the curve. And so now it asks us to find r prime of t. All right, so I think, let's see. Oh, I'll scooch it up later. All right, so if we're finding r prime, that means that we are just differentiating x and y with respect to t. So, all right, r prime of t will be, and I'm just going to do a little bit of work right above this since I have the room, right? If x of t is t, then we know that x prime of t is 1. if y of t is t squared plus 2, then we know that y prime of t is 2t. So these items right here, that's what's going to go into r prime, right? Those are our component functions for r prime. So r prime of t will be 1 I hat. I'll write the 1, why not? All right, plus 2t times j hat. Literally just x prime I plus a y prime j. Could not be easier. All right, and now this next part. I kind of like this next part because it's really going to drive home a couple of important points about not only vector valued functions, but vectors themselves. Okay, so I'm just going to try to scoot this up a little bit. All right, find and draw in r of 1. Easy enough. All right, so r of 1 means vector value function r evaluated when t equals 1. And in this case, all right, that is going to be, well, t is 1, so 1 I hat plus, right, t squared plus 2 j hat. So that ends up being 1 I hat plus 3 j hat. Okay. So that's wonderful. All right, we have found it. So now let's draw it in. And let's draw it in green. All right, so r of 1, I'm actually going to do in green. All right, so 1i plus 3j. So that is 1 over in the horizontal direction. All right, so let's scale this maybe a little bit. I'm just going to do, 1, 2. And then, okay, figure not drawn to scale. 1, 2, 3. All right, so at the end of the day, that is going to put us basically at the point 1, 3. So it's going to be a vector that has, right, 1 horizontal component and 3 vertical components. So that's going to be that vector right there. All right, so that right there is r of 1. Now it asks us to find r prime of 1. Okay. So r prime of 1 will be our derivative vector evaluated at t equals 1. Well, guess what? It's just 1 I hat. All right, so, right, that is 1 regardless of what t is. All right, plus 2 times t j hat. So that is 1 I hat plus 2 j hat. All right, and so let me add that in red. All right, 1 in the horizontal direction, 2 in the vertical direction. So this is r prime of 1. And this should maybe make you pause for a moment because that's great, right? Like we found our prime of 1, we drew it, but first of all, what did we just find? So that's the first question. So I would like you to figure out, right, if we just took the derivative of r prime and evaluated it at 1, like what does that mean for a vector? So I encourage you to pause, take a moment to think about that. I know you probably won't. All right, but if we think about what a derivative is, right, the derivative is the slope of the tangent line. So what we have just generated here is a tangent vector. All right, so this right here, okay, I'm going to sort of dot this. This is the tangent vector at t equals 1. Well, something should strike you as odd at this point, right? Because at t equals 1, we were directed to this point right here. Why does our tangent vector not look tangent to the plane curve? Well, the answer to that question, which you may already have, but the answer to that question lies in the definition of a vector, all right? So a vector is uniquely defined by its magnitude and direction. Nowhere in there does it say anything about position, okay? So what this means, right, if you recall, is that we can have many copies, in fact, infinitely many copies of that vector in red anywhere on the coordinate plane. And it's still just that one vector. So no matter, basically, translations of this vector, right, shifts up and down and around the coordinate plane don't change this vector. As long as it has the same magnitude and direction, it is the same vector. So I could very easily, very easily in my mind, shift this vector up to that point and make it look more tangent to that point, and it would still be the same vector. So I am going to do my very best to make this happen and explain everything. I'm not super confident, but I am going to take an academic risk. All right, so let's see. If I select this, okay, it copied it. All right, that's fine. And all right, there's a little bit of extra stuff in there that I don't want copied. All right, but maybe we could believe, right, that if we were to shift that vector up to that point, it would look a little bit more like it is tangent to the plane curve at the point where t equals 1. So that was all very roundabout. Obviously, my picture's not perfect. In a perfect world, that vector, would be, perfectly tangent at that curve. Looks like my slope's a little off. Okay. But hopefully you get the idea. So by finding r prime of 1, we have found the tangent vector at t equals 1. And so when we draw the vector in standard position, it doesn't necessarily look like it is tangent to the point in question, but just remember that position is not a defining characteristic of vectors. So you can move that vector all over the coordinate plane if you want to. It is still the same vector. And that's the big takeaway from there. So now on to one of those, sort of nitpicky topics for differentiation with vector valued functions. Really the one thing we have to be concerned with is smoothness of plane curves. But honestly, when we were doing differentiation, right, smoothness was an issue as well, right? Curves were not defined at sharp peaks, right? And so curves were not differentiable at sharp peaks. Well, we have to take that into consideration for plane curves defined by vector value functions as well. Now, when it came to, differentiating, like a regular function, how might we know that we potentially had a sharp peak at a particular point, right? Well, it would only really occur at places where the derivative was undefined, all right? So that's the same idea for curves defined by vector-valued functions. If a curve is not smooth at a particular point, right? So if it's pointy at a particular point, the vector will not be defined there. In other words, right, just like how at a sharp peak on a graph you don't have a derivative, at a sharp peak for a plane curve, you don't have a vector. All right, so that's why it says right here in this definition that, right, the curve is smooth if, x prime, y prime, and z prime are continuous, right, on whatever interval you're considering, and r prime does not equal 0, all right, for any value of t on that interval. All right, so let's put this into practice. All righty. So now We are given a vector in example 2. Notice we are only concerned about the interval 0 to 2 pi. And it wants to know, where is this curve smooth? Okay, so we know that it will be smooth, all right, anywhere where the component functions have continuous derivatives and anywhere where the derivative does not equal 0. So I think that's going to be our first line of defense, right? Let's get the derivative. So r prime of t. Okay, and so again, to differentiate this, we're just going to go component by component. So the derivative of 5 cosine t will be negative 5 sine t. And then this next one will differentiate to a positive sign, so positive 5 sine 5t, and that's your horizontal component. And so then if we continue differentiating our vertical component, let's see, that will be negative 5 cosine 5t, because we remember chain rule, always. Okay, and so now we need r prime of t to equal 0, which means that both components have to be 0. The x component has to be 0, and the y component has to be 0, right? If just one or the other is 0, that just means that we have a vector that is strictly in the horizontal direction or strictly in the vertical direction, and that's not a big deal. So we need both of them to be equal to 0. All right, so let's start with our x component. All right, so this has to be equal to 0. All right, so I'm going to divide out the 5, maybe rearrange some things to make it pretty. So let's see, we'll get sine 5t minus sine t equals 0. And honestly, I'm sure, you could bring your calculator into this. You could, maybe use some kinds of crazy identities to simplify this. But honestly, I feel like this is simple enough. We're only interested on the interval 0 to 2 pi. We can think about this. All right, so I recommend that you do. All right, and this will be true when t is equal to, well, definitely pi and 2 pi. And 0, of course. And let's see, I feel like it will also happen. Will it happen at pi over 2 and 3 pi over 2? Yes, it will. All right, so you can verify that. But this is what's going to work. Okay. All right, so now let's check the y component. Okay, so we need the y component to go to 0 as well. So 5 cosine t minus 5 cosine 5t. And so let's see, let's divide out the 5. And same approach, I think. Right, and so if we simply think about this, I know that this will be true. Let's see, well, obviously when t is 0, 2 pi. Does pi work? Yes. And then, it's going to work for your multiples of pi over 2 as well, because cosine will be 0. All right, so now, if it turned out that there were, solutions to this first one, like let's say, and maybe I missed some, I'm kind of jumping the gun because I know how it's going to work out, but let's say that there were another solution here, and actually I think there is, I think pi over 6 works here too, right? So there are others, I just kind of glazed over them. All right, but pi over 6 works here, right? Because the sine of 5 pi over 6 is equivalent to the sine of pi over 6. But guess what? That is not a value of t that is going to cause both components to go to 0. Okay? So something to keep in mind there. All right, so these are the places where the curve is not smooth. All right, and I would like you to see what's going on here. Because you can very easily list out those intervals. It's like, oh, so the curve is smooth from, 0 to pi over 2, from pi over 2 to pi, et cetera, et cetera. That is not the hard part. I would like us to see what is actually happening. So if we go and we sketch this, and this, this would probably take some time to sketch out. So I'm just going to sort of give it to you to help you out here. All right, we get something like this, and it's really cool. It's worth taking a look at. So let's see, this is 2, 4. All right, let's do the same up here. Okay, so if we sketch this out, let's see, when t equals to 0, you end up plotting this point. All right, and then basically, all right, you hit these points along the way, but you actually, so you start at the point 4, 0. So this corresponds with the point t equals 0. And we're going to go, and it'll, whoops, that was not the color I wanted. Let's do black. Here we go. Like this. It's a little something in honor of St. Patrick's Day, even though I have drawn it really not that well at all. It should basically look like a 4-leaf clover. All right, and so if we indicate our trajectory, we start there and we move around this way. Okay, and so this point here actually corresponds to t equals pi over 2. This corresponds to t equals pi. T equals 3 pi over 2, and so on and so forth. All right, so you can see that this curve has some peaks, right? Some sharp cusps, if you will, at those points. And so the graph is not smooth there. And actually, this shape has a pretty cool name. This is called an epicycloid. You don't really need to know that, but I think it's neat. All right, so that's a note on smoothness. Perhaps you can make your picture better than mine. Maybe do a little bit of, coloring in honor of the holiday. All right, I'm not going to go ahead and finish this whole thing. All right, but make your picture better than mine. That's the big takeaway there. So for now, on to integration. And again, the good news is integration, it works exactly the way that you would want it to work. We've just got to be a little bit careful. So just to bring you to these definitions up here, right? So if you have a vector valued function r, right, with component functions x and y, and you want to integrate it, you simply integrate each of the components individually. But you always remember your plus c, because we always remember plus c, right? And I would say that here's the thing to note. C is a constant vector. All right, so C is not just going to be a number. C is going to be a vector, right? So it's not just going to be like, oh, plus 4 at the end of it. It's going to be like plus the vector for -2 or something like that. It's like basically each component gets a constant of integration, and it's kind of up to you. You know, you can think of each of the individual components as having like a plus C, or you can just say like, oh, plus a constant vector at the end. All right. If we are looking at item number 2 here, right, this just gives you rules for evaluating definite integrals. And it's basically you just do the definite integral on each of the components individually, right? Because they're separate things, right? Each of them generates its own separate number that tells you the magnitude of each of the components of the vector, right? So we sort of evaluate them individually to be like, this is how far over you go. This is how far up your vector goes, etc., etc. All right. So you'll get the hang of it once we put it into practice, I think. All right. So let's take a look. All right. And when it says this extends to space curves as well, that just means you can do, 3 dimensions, and it's the same idea. Okay. So, all right, let's do example 3. All right. So it's a definite integral here. All right, so it has given us r of t equals, and then it's like some crazy stuff, and that's fine. But actually, it's not really that crazy at all. It just looks super intimidating, doesn't it? Also, a side note, why we would ever want to integrate or differentiate a vector, that's coming up in the next lesson. But, vectors, kind of a lot of motion-y ideas going on in there. So hopefully the idea of wanting to differentiate or integrate does not seem totally out of left field. All right, but let's get started. All right, so for any integral, all right, we first have to get an antiderivative. So this basically means integrate each component. And so I'm going to take the time to write this out. All righty. So notice, it's the integral of the component and then I hat. Okay? So it's like the integral of that number times I hat plus the integral of this piece, do not forget your dt's, times j hat plus the integral of this bit times k hat. Fantastic. So let's do it. All right, that's really a t to the 1/3. So when I integrate, I will get t to the 4/3 times 3/4 from 0 to 1. That is still attached to I. This is going to go to the natural log of t plus 1 from 0 to 1. And then this, will go to negative e to the negative t, evaluated from 0 to 1, right? And that attaches to your k component. Okay, so let's do the definite integral step. And you can see this sort of like, it becomes a lot of pieces. It's sort of like an exercise in bookkeeping, but conceptually, I don't think it's terribly taxing. All right, so when t equals 1, you get 3/4 times 1, so 3/4, and then when t is 0, you have 0. So I hat. When t equals 1 in the j component, you're going to get the natural log of 2, all right, minus the natural log of 0 plus 1. So that's minus the natural log of 1, which is also 0, plus, and then negative e to the negative 1. All right, so I'm going to say negative 1 over e. And then minus a negative, so plus e to the negative 0, 1. And then that attaches to the k component. All right, why I opted for brackets in that last one, couldn't tell you. All righty, so we've got 3/4 I hat plus ln2 j hat plus, I'll say 1 minus 1 over e k hat. And now I would like you to just think about, why do we not need a plus c at the end of all of this? Because it was a definite integral. So on the next page, we will do an indefinite integral, and we will need constants of integration and all that good stuff. But hey, for a definite integral, it's all good. And so in this next example, we will do the same thing. However, we've been given an initial condition. So all that means is that we can solve for the constant of integration. All right, but overall, it's not too bad. So the integral of RT dt will be equal to, well, we're just going to integrate each of these components. So let's see, dt I hat minus the integral of 2 sine t dt j hat plus the integral of 1 over 1 plus t squared dt k hat. Okay, so the antiderivative of cosine 2t will be sine of 2t, right, but over 2, because chain rule. So we'll say 1/2 sine 2t. And now here you have a choice. You can put in a constant of integration for this individual component, or you can put a constant vector at the end. All right, so I'm going to just proceed here, and I'll explain more about what that means. All right, so I've got basically a -2 times the integral of sine t. So sine t will integrate to a negative cosine. So ultimately this will become plus 2 cosine t j hat. And then this is looking like an arctan. All right, so this is going to be arctan t and k hat. And so now this is what I'm talking about. All right, you could do this a lot of ways. You could say plus some constant vector. All right, that's one way that you could do it. All right, I am just going to copy a bunch of this here so that I don't have to write it all out again. All right, so another way that you could do it is that you could say all of this and then plus, right, C1, C2, C3, and you do need different constants because each of those components might have a different constant of integration, and they will. All right, and then you know what, let's do that little copy paste, but actually, no, you know what, I'm going to write it all out again because the other way that you can write this is 1/2 sine 2t plus C1 I hat plus 2 cosine t plus C2 j hat plus arctan t plus C3 times k hat, right? All of those really mean the same thing, all right? And so it's up to you how you want to do it, but just be aware that there are multiple formats here. All right, so now we've got this initial condition, all right? And by initial condition, right, we mean t equals 0, all right? So that basically means when t equals 0, our antiderivative, which I am just going to call big R of t, all right, should generate that vector for us. So it's just a matter of, when I plug in t equals 0, each of the individual components work out to the appropriate number. For example, the I component should work out to be 3 when t is 0. This component should work out to be -2. And this component, when t is 0, should work out to be 1, right? So that's what we're talking about here. Okay, so, all right, so let's work that out. All right, so when t is 0, so 1/2 sine 0 plus C1, right? When t is 0, I should get out 3. Well, sine of 0 is 0, so at the end of the day, we're looking at C1 equals 3. Great. All right, on to the next one. All right, when t is 0, my j component should work out to be -2. So the cosine of 0 is 1. So I have 2 plus c2 equals -2. Therefore, c2 equals -4. And last but not least, all right, arctan, right, of 0 plus c3 should equal 1. Arctan of 0 is 0. Therefore, c3 equals 1. So again, I can give my particular solution in any number of formats, all right? I could say that my solution is, and now I am going to do that copy-paste thing again. All right, I'm going to come back. Oops. Maybe not. Okay, all right. Lesson learned. Don't be lazy. All right, 1/2 sine 2t I hat plus 2 cosine t j hat plus arctan t k hat, and I could say plus, and now my constant vector, 3, -4, 1, or I could lump those constants in with their individual components, right? I could say 1/2 sine 2t plus 3 I hat plus 2 cosine t minus 4 j hat plus arctan t plus 1 k hat. Up to you. They all mean the same thing, right? Because that's how we add vectors, right? We add horizontal component to horizontal component, vertical to vertical, etc., etc. So at the end of the day, it's a lot of bookkeeping. It's sort of a lot of legwork, but conceptually, I'd say this is fine, just fine. And in the next section, we will talk about like why we would ever want to do this. But let's be honest, this is BC Calculus. Why do we do any of this? For the fun. See you later.